I'm Choi from Sungkyunkwan University, and today I'd like to introduce about our recent work, SPARQ, hardware combining sparsity and quantization for LLMs. As LLMs grow, running them directly on devices like smartphones or desktops become more attractive. On-device inference offers fast response, lower latency, and stronger privacy. But to make this possible, we need compression and also hardware that can run compressed model efficiently without reversing the compression. We start with a full-size LLM that's too big and slow for most devices. There are many compression methods, but we focus on quantization and sparsity. These methods help reduce the model size without losing much accuracy. In quantization, there are two main types, weight-only quantization and weight activation quantization. And for sparsity, there are three methods, unstructured, structured, and semi-structured sparsity. Our objective was to focus on weight-only quantization and semi-structured sparsity and to design hardware that supports both natively. Like we said, we focus on hardware support for weight-only quantization and semi-structured sparsity. Specifically, in weight-only quantization, we convert 32 bits weight into 4-bit integer while keeping inputs and outputs in full precision. In semi-structured sparsity, we enforce a fixed pattern like 2 out of every 4 weights being 0, which make it easier for hardware to exploit. By supporting these two compression techniques in hardware, we can run LLMs more efficiently on resource-constrained devices. Before we combine these two techniques in hardware, we first look at their impacts on model accuracy. Here, we show the perplexity of dense floating-point 16 models as our baseline references. Perplexity is a standard metric for LLMs. Lower means better predictions. Applying either 2 for sparsity or weight-only quantization with integer full leads to a small accuracy drop, especially in smaller models. When we combine both techniques, weight-only quantization and 2 for sparsity, this drop becomes very similar to this drop in accuracy. It's a bit larger than using either one alone. However, as the model gets bigger, this drop becomes very smart to ignore. This motivates our design of SPARQ, a hardware solution that combines both techniques to maximize efficiency while keeping accuracy high for large-scale LLMs. We aim to design hardware that combines both techniques, but existing hardware platforms aren't ready to support them effectively. First, existing hardware only supports floating point by floating point or integer by integer, not mixed precision floating point by integer. Second, integer weights need to dequantize back to floating point, which adds overhead. Third, semi-structured sparsity isn't natively supported, so its benefits are often lost. That's why we propose SPARQ, a new architecture that addresses these limitations and enable efficient execution of compressed LLMs. Even though we want hardware to support compressed model directly, most existing systems still follow the standard full precision setup. In a standard transformer model, both the inputs and weights are usually in floating point. So our matrix multiplication operations in the linear layers and the attention block are done as floating point, floating point. If you look at the zoom-in attention block, every layer takes a floating point input, uses a floating point weight, and produces a floating point output. It's a completely floating point only pipeline. And what happens when we quantize weights to 4 bits? Existing hardware still only support floating point, not mixed precision floating point integer computation. So we have to dequantize integer weights back to floating point, adding overhead. That means we can't fully benefit from compression without native integer weight support in hardware. So we decided to support floating point by integer computation directly in hardware, which became the starting point of SPARQ. We designed a new map unit that takes floating point inputs and integer weights without conversion, so we can skip the quantization and actually benefit from quantization. But even if linear layers use floating point integer computation, not all operations can. Matrix multiplications in attention blocks still use floating point by floating point computation, so we also need hardware that supports full floating point computation. At the core of any accelerator is the matrix multiplication unit. Our design focuses on enhancing the MXU to support both quantization and sparsity at the same time. This is our baseline MXU app using a systolic array for floating point computation. It works well for full precision LLMs, but becomes a bottleneck when weights are quantized to integer. That's why we need something more flexible module. Integer 4 weights are streamed in, and floating point inputs stay inside the PE. Each P performs floating point by integer and accumulate in floating point. This module knows the quantization needed. And last, this is MXU SI module, our final design. It extends MXU I with structure changes to support end-to-end semi-structure sparsity. So here we show the overview of SPARQ. SPARQ combines MXU F module for floating point by floating point and MXU SI for integer weights with end-to-end sparsity. This enables efficient support for both metmer and linear layers in LLMs. Typical systolic arrays follow either weight stationary or input stationary data flows. For example, Google TPU use weight stationary. This slide shows how weight stationary works. Weights stay inside PEs and input flow across. It's fine for dense model, but with semi-structured sparsity, zeros are still processed wasting cycles. Now let's look at the input stationary data flow. In this setup, the inputs stay fixed inside the PEs and the weights are streamed in. For dense model, this isn't much different from the weight stationary approach because our weights are using anyway. But when we compress weights like in semi-structured sparsity, we can skip the zeros and only fit in non-zero weights. That means fewer mag operations and we can actually see real speedup. And that's exactly why we choose input stationary systolic array for our architecture. Now that we've seen why input stationary is a better fit for sparse weights, and let's dive deeper into how this works inside the MXU SI modules. Here's a simplified view of two PE rows in our input stationary design. While this helps skip zeros, new challenge arrive when we apply end-to-end sparsity, which we will walk through next. Let me walk you through a simple example. We multiply an 8x2 sparse weight matrix with a 2x1 dense input vector. This produces an 8x1 output, and we'll use it to highlight execution time completes. This slide shows how 2-to-4 sparse gem works using an input stationary systolic array. Each weight row follows a 2 out of 4 sparsity pattern, meaning only 2 weights are non-zero. The inputs stay fixed in the PEs while the weights move horizontally across the array. At each step, the P performs a multiply and accumulate operation between the input and the incoming weight. The result is a partial sum, which gets passed down to the next P in the following row. As weights continue to move and max are computed, the final output building up gradually through these partial sum accumulations. Here's the sample we've been using. Let's focus on output 01. It's computed from 2 zero weights multiplied by inputs I0 and I1. Now, if we apply model compression and remove these zeros, 01 can't be computed anymore. So even if sparsity helps reduce the model size, we still need to ensure our outputs like 01 are properly handled. In the baseline design, output like 01 can be missed when our corresponding weights are zeros. To fix this, we add a skipping path that ensures our outputs are accumulated properly, even with sparsity. This guarantees correctness is preserved without losing any outputs. Now, this example also shows another key issue. In the uncompressed model, output O2 accumulated weight B multiply I0 and weight C multiply I1. There are no conflicts. But with 2 to 4 complete compression, weight B moves to second slot and weight C to the first, shifting their timing. Due to systolic flow, C arrives one cycle later, so both B and C try to update O2 at the same time. So this creates a data hazard. We can't accumulate both to P2 in the same cycle. Let's take a closer look at what happens when the compressed weights are fed into the same input stationary architecture. The initial setup looks the same as before, but as the cycle goes on, two conflicts start to appear. As we move from cycle 1 to cycle 2, a conflict appears in input stationary 2 to 4 sparse execution. Here, P2 needs to be processed by two PEs at once, which cause contention. This shows that sparse weights need smarter handling of partial sum timing and routing. To resolve the earlier conflicts, we add an inter-P buffer between rows. This buffer stores partial sum temporarily, so they don't need to be processed right away. It prevents collisions and supports faster timing under sparse weights. We added an inter-P buffer and skipping paths to solve earlier partial sum conflicts. But now, multiple partial sum may arrive out of order, and we need to decide which path to take, accumulation path or skipping path. To handle this, we use sparse pattern indicator called SPI. For example, if a weight group has non-zeros at index 0 and 3, the SPI generator produces metadata, A path for accumulation and S path for skipping paths. When this group enters the buffer, SPI guides P0 to accumulation path and P1 go to skipping path. The same logic applies for P2 and P3. This way, partial sum are routed correctly, even under semi-structured sparsity. This slide shows the high-level architecture of SPARQ. MXUF handles standard floating point operation, mainly used for attention block in merged layers. And MXUSI supports floating point input and integer weights with end-to-end sparsity, and is designed for linear layers. Together, they enable efficient execution of both dense and sparse computation in LLMs. This table summarizes the area and power of the three MXU types used in SPARQ. Compared to MXUF, MXUI reduces both area and power by about 25% by removing full precision multipliers. MXUSI adds some overhead, 43% more area and 49% more power, but supports end-to-end sparsity, giving double throughput. And the RTL implementation of MXUSI modules in publicly available as part of our architect. This slide shows the relative inference time with different MXU configurations. The results are normalized to the baseline setup with 4 MXUF. As we reduce the number of MXUF, attention blocks slow down since they rely on floating point, and can't exploit sparsity. But adding more MXUSIs speeds up linear layers that benefit from quantization and sparsity. All in all, inference time depends on the balance between attention and linear layers. For example, in a PT66 billion model, using one MXUF module and 3 MXUSI module reduces latency by 26%. This shows that for large model around 1 billion parameter and above, SPARQ deliver real performance gains. And this chart shows relative tops per square millimeters, again normalized to our baseline for MXUF setup. For smaller model, we don't see much gain because they rely more on matrix multiplication from attention blocks, which only run on MXUF modules. But as model get larger and linear layers start to dominate, the advantage of MXUSI becomes more obvious. For instance, on OPT66 billion model, The setup 2MXUF module and 2MXUSI module improves area efficiency by 33%. And on Bloom 7.1 billion model, we see up to 53% higher efficiency with 1MXUF and 3MXUS in setup. So our MXUSI module doesn't help everything. It gives area benefit when the workload is right, especially when there's more linear computation and sparsity to exploit. In energy efficiency, measured in TOPS per watt, just like we saw with area efficiency, the benefit of MXUSI becomes more noticeable as model size increase. Smaller models still rely heavily on matrix multiplication, but once we pass 1 billion parameters, the linear layers dominate, and that's where MXUSI shines. For example, OPT 13 billion model achieved a 51% increase in energy efficiency when using the 1 MXUF and 3 MXUS setup compared to the baseline 4 MXUFP setup. Here's how SPARQ stacks up against another prior work, Figna. If you look at the number here, one thing immediately stands out. With SPARQ MXUSI, we achieve 1.79 higher area efficiency than Figna. That's a huge jump in terms of how much performance we get per silicon area. And even more impressive is the energy delay product called EDP. SPARQ MXUSI achieves a 5.27 lower EDP than Figna. In other words, we are not just faster, we are way more energy efficient at the same time. All in all, SPARQ delivers much better compute efficiency without sacrificing performance or energy. So to wrap up, here's the key takeaway. SPARQ improves LLM inference efficiency by using a hybrid architecture that combines MXUF and MXUSI. This allows us to handle both dense and sparse workloads efficiently, whether it's matrix multiplication in attention or linear layers with quantized weights. By doing so, we can fully exploit quantization and structure sparsity, achieving better performance, energy efficiency, and area efficiency, all at the same time. Thank you for your attention.
Okay, thank you for the great talk. So, do we have any questions? Okay, it's no more. I mean, actually, I have several questions, but can you go back to the evaluation slide for the, for any one of the, it might be, okay. So which means that the best configuration will change depending on your target models.
Yes.
So therefore, my question is that, should you assume to use the FPGA, or will you use some kind of the ASIC chip? So which means that when you change the target model, how can you find the best configuration? So it depends on the model, and model characteristics will change over the years.
Yes.
Okay.
In our work, we just focus on not configurable architecture, and just how we fix architecture MXUF and MXUSI modules different configuration, and when we change the configuration, we have this result for many large language models. So in our future work, we make a configurable architecture for LLM models. So, yeah.
So is there no takeaway for this kind of the evaluation study? Okay, that's fine. Okay, and another my question here is that you mentioned that input stationary is good for this kind of the accelerator.
Yes.
How about the other previous work? Do they use the weight stationary so far? Is this your novel approach in this work?
I think for this work, input stationary is best techniques for make hardware architecture for LLMs support quantization and sparsity, but when we use another comparison techniques or another hardware setup, so input stationary is not best techniques, I think. But in this work, input stationary is.
How about other approaches? Do they use the weight stationary so far? Okay, that's fine. I have another several questions, but we don't have enough time. So thank you again for the great talk, and we will. Oh, sorry. I have really narrow scope.
I have one question on the same slide.
Oh, yes.
So the slide shows us about like performance varies around configurations.
Yes.
Then my question is, so what configuration?
This configuration
Well,
for.
what is the
yes.
size of each array and how many arrays? So in this case, you are assuming that like, so you actually have 4 different arrays and
Yes.
2 MXUF and 2 MXUXI.
Yes.
It seems that that combination is better in almost all cases. Right?
Yes.
And it does not depend on the size of array, or why don't you use like number of more arrays?
First, our configuration of MXUSI and MXF module for SPARQ. Every MXU module have 64 by 64 PE.
Okay.
And we have 4 MXU in SPARQ architecture for this work. And because of this configuration, we check difference with previous work like Figma or another post LLM accelerator. So we choose configuration like this.
So does it mean that you use like 50% of utilization of array for like, so when you are performing some integer and floating, then you use only 2 arrays, and for other ones then you have only 2 arrays. So how do your utilizations? So in your proposed approach then, how do your utilization is only 50%?
Yes.
So, okay. But still it is better, like if we have 4 MXUF and
Yes.
we do not actually we use dequantization, like
Yeah. Yes.
then we can use the whole architecture fully,
Yes.
right? But still, you are saying that like 50% of hardware utilization is better
In the quantization LLM models.
without the if your proposed approach is
yes.
not use dequantization, right?
Yes.
But you actually sacrifice hardware utilization by 50%.
Yes.
Right? So if you add the dequantization block and we use full MXU minus F hardware block,
Yeah.
then you increase the utilization 100%.
Yes.
Right? So, but your proposing says that like, so 50% utilization is still better
Yes.
in terms of inference speed. Is that right?
Yes.
Okay. So,
Okay.
I understand that your proposed approach will be better in terms of energy consumption, for sure.
Yes.
But my question is about inference time.
Inference time.
Yeah, inference time only. So if we use
It's not.
100%.
It's not for our LLM models for use that no dequantization in models.
So if we use
Yes.
dequantizer and we use only floating point arrays only,
Yes.
right? Then you can utilize 100% hardware.
Yes.
Because all matrix multiplications or linear operations are floating point operations.
Yes.
But your proposal approach seems like hardware utilization will be only 50%.
Yes.
So that is my question. So still, okay.
Yeah, you can talk offline then. Okay. Okay, thank you.